Hello everyone, this is Ahmed Inaya. In this video, I will talk about Cisco switch, MAC table and ARP protocol. Let's start by talking about the main functions of a switch. Switches forward frames or layer 2 BDUs between hosts based on MAC address, and we will discuss MAC address in coming slide. Switches learn MAC addresses by examining source MAC address of sending host, and they build loop-free topology with other switches, and this is called spanning tree protocol or STP that we will discuss in coming video. Let's take a look at an example of layer 2 frame, which is Ethernet frame 802.3. This is one variation of Ethernet frame. The unit in this frame is octet or byte, which is 8 bits. As we discussed before, computers send and store information as bits. Usually, we use byte when we talk about storage, and we use octet in many other cases. So this is the format for a frame. It has these different fields. It starts by preamble. Preamble is 7 octets, 7 bytes or 56 bits. It provides bit level synchronization. So before hosts start communicating, they need to synchronize, which means they need to make sure that their clocks start at the same time and using the same frequency. This is called synchronization, and it is needed to make sure that all devices in the network knows exactly when every bit starts and when it ends. So preamble makes receiver ready before start sending MAC addresses. Sometimes preamble is not considered as part of the frame, but it is sent before every frame to make sure that all stations are synchronized and their clocks start at the same time and they know exactly the start and the end of each bit. After preamble, we have SFD, which is 1 byte or 1 octet. SFD stands for Start Frame Delimiter. It marks the end of the preamble and it has the binary value of 10101011. So when receiver sees this value, it knows that the next octet or next byte is the start of destination MAC address. After SFD, the actual Ethernet frame starts. It starts by destination MAC address, which is 6 bytes long or 6 octets, and destination MAC address is used by switches to decide how to forward the frames, as we will see in the coming slides. Destination MAC address can be unicast, multicast, or broadcast, and we will discuss the difference between these MAC addresses in the coming slide. After destination MAC address, we have source MAC address, which marks the MAC address of sending device. It is also 6 octets or 48 bits, and for switches, it is used to learn MAC addresses of different devices. After source MAC address, we have Ethernet type, which is 2 bits or 2 octets. There are many types of Ethernet, but the main types are IPv4, ARP, and 802.1q. Based on Ethernet type, the receiver will know how to understand the data or the payload of this frame. The data or payload itself may have another headers, as we discussed in the first video, but for Ethernet or for layer 2 frame, all this is data or payload, including headers within this data. Data can be any value from 46 to 1500, and it can be more in some cases, but the minimum is 46 bits. If data is less than 46 bits, or if the frame size is less than 64, padding will be added to make data reach the minimum value of 46 bits, or to make the frame 64 bits at least. After data and at the end of the frame, we have FCS or frame check sequence. This is 4 bytes or 4 octets, and it is used for error detection code. So receiver end can verify the integrity and correctness of the frame based on this FCS value. So before going deep into switching, let's discuss MAC address. What is a MAC address? MAC stands for Media Access Control. It represents the physical address for network hardware. It is 48 bits, which is 6 bytes or 6 octets, and it is divided into 2 parts. The first part, which is 24 bits, is called OUI, or Organizationally Unique Identifier. The other 24 bits are assigned by vendor for this hardware or this interface. Usually, it is represented in hexadecimal, So 48 bits is equivalent to 12 digits hexadecimal. This is because hexadecimal is base 16 and bits are base 2. And as we discussed before, every digit hexadecimal can be mapped to 4 digits. Every digit hexadecimal can be mapped to 4 digits binary. So representing MAC address in hexadecimal makes it shorter and easier to read and understand. Instead of typing it as 48 bits, it is much easier to write the MAC address as 12 digits hexadecimal. MAC address goes by many other names, like burned in address. This is because manufacturers usually burn in this address into the hardware. Sometimes it is called Ethernet address because it is used mainly by Ethernet protocol, and in some cases it is called hardware address because it is attached to the hardware and it is unique per hardware. There are different types of MAC addresses. First, we have broadcast MAC addresses, which means all devices in this network now. Broadcast MAC address is defined by all if hexadecimal, which means all ones binary. If hexadecimal equals 1111 binary. So 12 digits hexadecimal, all with the if value, means we have 48 bits binary, all with ones. So if destination MAC address is a broadcast address with all if, this means this frame is meant to be sent to all devices in the network that are active now. So in binary format, this is all ones, 48 bits, all ones in binary format, or in hexadecimal, it is all if, which is the same as all ones binary. The other type of MAC addresses is multicast MAC address, which means certain group of devices in this network now. Details of multicast are not part of this course, but for now it is enough to know that multicast MAC addresses, they have the last bit of first octet as 1. So if this is the MAC address in binary format, if the last bit of first octet is 1, this means this is a multicast MAC address and only devices that are part of this multicast group are interested to receive this traffic. So to identify multicast MAC address, you need to look at this bit of the binary format of MAC address. For example, this MAC address is multicast. It is used by Cisco devices to discover other devices in the network. This is called CDP or Cisco Discovery Protocol, and it is used by Cisco devices to identify neighboring devices and collect information about them. We will talk about CDP in the coming videos, but for now it is enough to know that this is a multicast MAC address because the last bit of the first byte is 1. If you convert this 01 hexadecimal into binary, it will be 0000 for the first 0 and 0001 for 1. So the last bit of the first byte is 1. So this is a multicast MAC address. The third type of MAC addresses is unicast MAC address, which identify single network interface or single device in the network. This is the MAC address for any device connected to the network. So any PC, any laptop, or any phone connected to the network should have a unicast MAC address to identify this device. This is an example for a MAC address, and we will see more examples in the coming slides and in the coming videos in this course. So after we discussed Ethernet frame and MAC addresses, let's talk about MAC forwarding process in Cisco switches. When a switch receives traffic, it looks at destination MAC address. Switches decide how to forward the frame or filter it based on destination MAC address. So based on that, they can take one of two decisions, whether to forward it to certain ports or maybe to filter it from other ports. So the decision whether to forward it or to filter it at every port is all based on destination MAC address and the information available to the switch at that time. We will talk more about this process in the coming slides. So if destination MAC address is a broadcast MAC address, which is all if hexadecimal or all one binary, the traffic is flooded to all interfaces. Because this destination MAC address means that this frame is meant to be sent to all devices in this network, so the switch will take this frame, will replicate it, and will send it to all devices that are active in the network now. If destination MAC address is a multicast MAC address, which means if the last bit of first octet is 1, In this case, layer 2 switches by default will float multicast traffic to all active devices in the network. Now, there are other protocols that may help in optimizing or filtering multicast traffic, for example, IGMP snooping, but this is not part of this course. And within the scope of this course, you can consider multicast traffic to be forwarded to all interfaces that are active in the network now. If destination MAC address is a unicast MAC address, which is the typical scenario, we have two options in this case. First, if the switch knows exactly where is the location of this destination MAC address, it will forward the traffic to that interface only because it is destined to that certain device, and there is no need to send this traffic or this frame to any other device in the network. But if the switch has no idea about the location of that destination MAC address, in this case the switch will float the traffic or the frame to all interfaces because it has no idea where is the location of that destination MAC address. So with time, switches build MAC address table for known MAC addresses, and they forward unicast MAC addresses based on this table. Let's look into the details of building MAC address table because it is one of the main functions of switching, and it is important to understand this process. When starting the switch for the first time, the MAC table is empty because the switch has no idea who is connected to every interface of the switch. The switch listens to traffic from different interfaces and it reads source MAC address in Ethernet frame to build its MAC table. So it maps source MAC address in Ethernet frame to the interface from where that frame was received. The next slide will talk about this process in more details. The same concept applies to links between switches, as we will see in the coming slide. If there is no traffic from that device for a certain time, the switch deletes this mapping or this MAC table entry. This is to make sure that MAC table is up to date. The switch keeps updating the table and it keeps deleting entries for devices that are not active or not connected currently to the network. The timeout period is called aging time. So for example, if aging time is 5 minutes for example, this means if no traffic received from certain device for 5 minutes, the switch will delete the entry for that device. We will talk more about aging time and MAC table in the next lab, which is lab 2 of day 1. You can add static MAC addresses to certain interfaces to make them permanent. The same way, MAC table can be cleared by command, and this is needed in some cases when you think MAC table is corrupted or when you make big changes in the network and you need MAC table to be updated immediately. Before going deep into MAC learning process and how switches build MAC table, let's discuss address resolution protocol, which is ARP. ARP protocol is important in MAC learning and MAC table process, and that's why it is good to understand how ARP works before we discuss MAC table building and before discussing MAC learning process in details. So usually applications and users communicate using IP addresses and not MAC addresses. IP addresses are logical addresses that work at layer 3 of TCP/IP model or network layer as compared to MAC addresses, which are physical and they work at layer 2 or data link layer of TCP/IP model. We will discuss IP addresses and IP subnets in more details in day 2 of this course. So devices in the same network communicate over Ethernet using MAC addresses, while applications and users communicate using IP addresses. So there should be a way to map IP addresses to MAC addresses, and for devices to get MAC addresses of certain IP address, they use ARP messaging or address resolution protocol to map IP addresses to MAC addresses, as we will see in the coming slide. For switches, although they don't care about IP addresses and although they work at layer 2, they use ARP messages to build their MAC table because ARP messages are exchanged immediately when devices connect to the network and when they need to communicate with each other. So before any communication between devices, they need to exchange ARP messages to find the MAC addresses of each other, and for the switch it is a good way to learn MAC addresses quickly and to build its MAC table. Let's look at this animation that helps in understanding how switches build MAC table and how ARP messages are exchanged between devices in the network. Let's assume this device 172.16.01, which is the IP address for this device, wants to communicate with this device here, which has the IP address of 172.16.03. Let's assume this is the MAC address for this device, and this is the MAC address for the other device. Now, these devices have no idea about the MAC address of each other, but they know the IP addresses of each other. So for this device to communicate with this IP address, it needs to send the traffic to the MAC address of this device. But how to find the MAC address of this device? This is why we need ARP protocol. From the switch perspective, the switch has no MAC entry until now, and the MAC table for the switch still empty with no entries at all. Builds this Ethernet frame, and in this frame the destination MAC address is broadcast because it has no idea what is the MAC address of this device. For source MAC address, it adds its own MAC address, and for simplicity I wrote this MAC address as 200.111. So instead of typing the full MAC address, I represented it by 0200.111 to save some space in my drawing. In this Ethernet frame, the payload include ARP details, and in ARP details or in ARP payload or ARP data, there is a message that says, I want to know the MAC address for this IP address. So device 1 sends this frame to the Ethernet switch. So device 1 sends this frame to the switch, and the switch uses source MAC address in Ethernet frame to map this MAC address to the interface from where this frame was received. So by receiving this frame, the switch was able to add the first entry in its MAC table, and this entry includes the source MAC address of this frame and the interface number from where this frame was received. Now, because the destination MAC address in this frame is FFF, which is a broadcast MAC address, the switch sends this frame to all interfaces that are active now. The other switch here forward the traffic from Fast Ethernet 024 to Fast Ethernet 01 because it is a broadcast and should be sent to all active interfaces in the switch. So all these devices will receive this Ethernet frame. Now all devices will look into the frame and will read the ARP message within this frame. Because ARP message looks for this IP address, this device will neglect this ARP because the IP address doesn't match the IP address in ARP request. This device will ignore this frame because again the IP address for this device is different than the IP address in ARP. For this device here, the IP address of this device equals the IP address in ARP request. So this device will process this ARP request and will reply to this ARP request. In its reply, the destination MAC address will be the same MAC address of the device that sent ARP request, because this device knows exactly who sent this ARP request. As we discussed before, the source MAC address in ARP request is a unicast, so this device knows that in ARP response I should reply to this MAC address, so destination MAC address is a unicast. For source MAC address, it is the MAC address for this device, and again I wrote it as 0200.333 for simplicity to save some space in my drawing. And in ARP reply, this device says that I have the IP address you are looking for, which is 172.16.03. Now this device sends this Ethernet frame to the switch, and when the switch receives this Ethernet frame, it looks at destination MAC address, which is a unicast in this case, and the switch looks into its MAC table. It has an entry for this MAC address, and this MAC address is connected to Fast Ethernet 01. So there is no need for the switch to send this MAC address to all interfaces because this MAC address is known to the switch and it knows exactly the location for this device and the interface where it is connected. So the switch forwards this frame to fast Ethernet 01 only to be sent to this device only. At the same time, the switch reads source MAC address in this Ethernet frame and maps this source MAC address to the interface from where it was received. So the switch now adds the second entry in its MAC table, and in this entry it includes the MAC address for this device and the interface from where the frame was received, which is Fast Ethernet 03. So the switch was able to add two MAC addresses as a result of this ARP messaging exchange between this device and this device. Now let's assume this device here wants to communicate with this device here. So this device with the IP address 172.16.02 wants to communicate with this device here, which has the IP address 172.16.04. This device has no idea what is the MAC address for 172.16.04, and in this case it will use ARP messaging to find the MAC address for this IP address. So it will start by building this Ethernet frame, and in this frame the destination MAC address is broadcast because it has no idea what is the unicast MAC address for this IP address. The source MAC address is the MAC address for this device, and in the ARP message it says what is the MAC address for 172.16.04. Now when the switch receives this message, it forwards it to all interfaces because destination is a broadcast MAC address, and this switch will replicate this message to Fast Ethernet 01. The switch looks also into the source MAC address and map it to the interface from where this frame was received, so the switch adds this entry into its MAC table. Now every device of these looks into the ARP message and reads the IP address within the ARP message. So for this device, the IP address in ARP message is different than its IP address, so it ignores this message. And for this device here, the IP address in ARP message is different than its IP address, so it ignores this message. But for this device, its IP address is the same as the IP address in ARP request, so it prepares ARP reply, and these are the details of this ARP reply. In this ARP reply, the destination MAC address is the MAC address of the device that sent this request. The source MAC address is the MAC address for this device, and in ARP reply it says I have the IP address 172.16.04. Now this device here sends this frame to the switch. So the switch looks into the destination MAC address. It is a unicast, and both switches has entry for this unicast MAC address, so they send the traffic directly to interface 02 in this switch to be sent to this device. At the same time, this switch reads the source MAC address of this frame and adds this MAC address into its MAC table, and for this switch here, it receives this frame from Fast Ethernet 024, so it adds this MAC address to its MAC table and it maps it to Fast Ethernet 024 because it is the interface where this frame was received. This way, this switch was able to build MAC table for these four devices by listening to ARP messages exchange between these devices. And the same process repeats whenever the switch receives messages. It keeps listening to source MAC addresses and it keeps adding to its MAC table. At the same time, the switch adds aging timer to these MAC addresses, and after some time it deletes these MAC addresses if the device is inactive and not sending any traffic for a long period. If you find this video useful, please don't forget to like this video, comment below, share this video to your friends and whoever interested, subscribe to my channel to receive my future videos, and enable notifications to know about my new videos. Thank you and have a good day.